Alright, let's get started. So, at the end of lecture Wednesday, we actually started getting into real enolate and enol chemistry. And the first chemistry we really talked about was the reaction between an enol, in this case, or an enolate with X2, such as Cl2, Br2, or I2. And so, just to give you an example, if you take a ketone or an aldehyde, under acidic conditions, we get a tautomerization, right? Where we can go from the ketone form to the enol form. Keto to enol. And I drew a normal arrow, but really it should be an equilibrium arrow. It's Cl2 for now. Alright, so under acidic conditions, and we went over this mechanism on Wednesday, we can go from the keto to the enol form. And enols are nucleophilic at carbon because of the resonance structures we drew on Monday, which is where you can think of this enol almost looking like this resonance contribution that puts a fair bit of partial minus charge at the alpha carbon. And so with enols, this partial minus charge can now attack nucleophiles, or protons. And in this case, in the haloform reaction, the enol attacks X2. So Cl2, Br2, I2, etc. And so what that gives us, at least in the enol mechanism, is an intermediate like this where we now put a chlorine in the on the alpha carbon. So we replace one alpha hydrogen with one alpha halogen. So hydrogen per halogen. So the thing about this chemistry is, if you let it, it will go as many times as it can. So if you're just doing one equivalent of X2, you'll get your monochlorinated product. Yes?
If you put HCl in the beginning with H3Os, would it just happen in one step?
No, you need electrophilic Cl2 source. HCl, after the protonation, will give you Cl minus, and Cl minus is not going to be electrophilic. You need an electrophile, so Cl2, yeah. Yes?
Is that one supposed to be resonance, the bottom one?
Yeah, this is just resonance structure by the resonance arrows. So, if you throw in one equivalent of Cl2, it will stop lines. But if you throw in excess equivalents of Cl2, or more generally your halides or diatomic halides, so X2, it will go as many times as it can. If there's two hydrogens, it will go two hydrogens. If there's three hydrogens in a methyl group, it will go all the way. So, one equivalent, the product you'll get will be upon quenching of this positive charge with water formed. So we know this is super acidic, so the water formed in the solution can easily take this proton. We'll get the monohalogenated. However, if you use excess Cl2, this mechanism will repeat itself until there's no more alpha hydrogens to chlorinate. And so, for example, what I usually do here, so this mechanism is going to occur 2 more times because there's 3. And so what I usually do when I draw the mechanism is I write something like repeat. I guess in this case it'll be 2 more times. Repeat 2 times. So then we form the enol, enol attacks Cl2. We form the enol again, enol attacks Cl2. So mechanism is the same. And so in an exam, don't feel like you have to draw the same mechanism over and over again. Unless you want to. Myself and the TAs are more than fine with you drawing the mechanism correctly once and then say rinse and repeat. And so eventually what that will give us, with excess Cl2, will give us the trichlorinated ketone. And of course, if this R group was a methyl, that would go as well. But in this case, let's make this an unreactive R group. And so now that we made this trichlorinated methyl group, something interesting happens. And that is now trichlorinated methyl groups, or alkyl groups, are good leaving groups. So this is now a good leaving group. And I'll explain why in a second. So we form this. There's acid around. So we can definitely protonate this. Since this is protonated, it's very electrophilic, so water can add in. This is an acetal mechanism, right? Water adding into this ketone is just a classic acetal mechanism. And when we're doing this chemistry in H3O, we're swimming in water, right? So then, normally we talk about maybe doing a intramolecular proton transfer, but in this case, let's just do an intermolecular, where one of the water molecules swimming around grabs the proton to give us our acetal. I'm tempted to just erase it and do magic board chemistry, but I know students don't like that, so I'll just draw the deprotonated intermediate. All right. And so typically with the ketone, you form the acetal, and that's what you get out, depending on your conditions and Le Chatelier's theorem. However, CCl3 is actually a pretty good leaving group. I believe its pKa is somewhere in the 20s-ish. Check the book, check the notes. I actually left my notes in my office. But I believe this is about a pKa of about 20. So anyway, trihalogenated carbons, methyls, are good leaving groups, just like an alcohol is a good leaving group. Water is a good leaving group. Amines can leave as well, right, in amide hydrolysis. So in this case, you might need a little bit of heat. But you can have an equilibrium where you kick off CCl3. So, yes, I know, this is a carbanion, but it's a carbanion with 3 electron withdrawing chlorines, right? So let me actually draw it as the carbanion in a planar form. So the reason CCl3 or CBr3 or CF3 or CI3 is a good leaving group is because halogens are electron withdrawn. And when this leaves, we have CX3 minus, but this minus charge can be electronically withdrawn by these 3 chlorines, right? So through the inductive effect, so these electronegative chlorines can spread out this minus charge in the carbon through LL3. So that's why they're lower pKa and more stable. And so what really actually drives this reaction though is, yes, this is a stable anion, but it's still basic. This is, let's say this is basic as in the mean, roughly. And so what drives this equilibrium to the product is the CCl3 minus being protonated to give chloroform. So chloroform plus, let me do the colors correctly, plus our carboxylic acid. So the net transformation I'll highlight in orange is in this corner. Or a methyl ketone plus excess Cl2 under acidic or basic conditions, right? For most things, anything you do under acidic conditions through the enol, you can do under basic conditions through the enolate. That's going to change once we get to later on in the chapter, and then we're going to focus specifically on the enolates. But the haloform reaction, or the scrambling of a stereocenter alpha to a carbonyl, you can do through an enol or an enolate. So the net transformation, though, is a methyl ketone excess X2, like Cl2, H3O, a little bit of triangles, there's some heat, and then what you'll get out will be the carboxylic acid. And this equilibrium is driven to the product because we form chloroform. So when the leaving group comes, it quickly protonates to give chloroform, which is fairly stable solvent. So just to show you an example of the basic conditions, yes?
So on the right side, where it forms the trichloro?
This guy?
No, the bottom right. Right there.
Yeah.
So when would it stop there? Would it ever stop, or would it have to have to be water present?
If you do it at room temperature. So you need heat. So this forming this anion still needs a bit of cushion. So if you do it under room temperature or cold, you will probably stop here. Well, do the trihalogenate product. So, but to get haloform, you need a little bit of pushing, so some heat. So to answer your question, room temperature, it will stop here. So just to show you an example of the basic conditions. So this is the acidic haloform. We use sodium hydroxide and sodium hydroxide and some heat, try some triangle, and excess X2. So when you heat this reaction up, I don't know why I wrote an A. So when you heat sodium hydroxide excess halogen, excess X2, that would be a great exponent title. And you heat it up, what you get out will be the carboxylate. And so I don't want to go through the mechanism exactly verbatim. Well, I don't want to go through the mechanism in its entirety, so it'll take a while. And it's not that simple. Well, it's simply the acidic one, just the enolate instead of the enol. And I feel like I have to leave you guys something to study for an exam. Don't stop the camera, but I think I just said something. At least you can look at the practice exam from last year, semester. And so anyway, under these conditions, we'll have some kind of equilibrium under basic conditions between the methyl ketone and the sodium enolate. So will this equilibrium be favoring the ketone or the enolate under sodium hydroxide? So under sodium hydroxide conditions, which one of these is going to be favored? Well, what's the pKa of sodium hydroxide? It's conjugate acid. About 16, 15.7. What's the pKa of a typical enolate? We've discussed a couple of times. I gave you guys a magic number on Wednesday for typical enolates.
20.
Yes, about 20 to 24. So, knowing if this is a pKa of 20-ish, and this has a pKa of 16, where's the equilibrium going to lie? The ketone, right? What can we do that causes equilibrium to favor the enolate? Okay, well, great. So add excess sodium hydroxide. So if we have excess sodium hydroxide, that will help us find the equilibrium, the enolate. And now the enolate is going to be more reactive than the enol because it's got a minus charge, so it's going to be more nucleophilic. So we'll attack X2 to give us this. We do it 2 more times. They get a trihalogenated ketone. Then one of the hydroxides is going to just go and add in, giving us a tetrabutyl intermediate, which quickly collapses. Plus CX3 minus. And then the thing that drives this mechanism forward is the fact that this is a carboxylate, right? So this step, this is just like a saponification mechanism, just instead of a methyl ether, it's a CX3. You guys see that kind of analogy? This step here is just a saponification mechanism. And so just like the saponification mechanism, it's driven forward by... So going from a methyl ester to a carboxylic acid I guess the week before spring break, what drove that equilibrium towards the product rather than the starting material? Going from methyl ester to the carboxylate. The thing that drove that mechanism forward, remember, was the deprotonation of the carboxylic acid to give you your carboxylate. So going from a methyl ester to a carboxylic acid, the thing that drives that equilibrium under basic conditions is the deprotonation of the carboxylic acid by the base. So in this case, the thing, and that's something you need to know. I'm not going to go over it because I've gone over it twice and it's been gone over in the lab, and it's something you guys should know at this point. And definitely study it, because that is a core reaction from this class that we've gone over many times. But just like in the saponification mechanism, where the leaving going from a methyl ester giving up MEO minus as a leaving group, and that deprotonates the carboxylic acid to give us a carboxylate to drive the equilibrium, this is going to do the same thing. Where the CX3 minus is going to act as a base, deprotonating this, giving us our carboxylate. plus HCX3. And this is just going to sit around until we quench it with H3O to get our carboxylic acid product out. So this part is highly analogous to the saponification mechanism. And just to remind you what the saponification mechanism is, because I'm getting a lot of blank faces and that worries the heck out of me. I know it's a nice day and a Friday. So going from an ester to a carboxylate. And then furnating it to get our carboxylic acid out. That is the saponification mechanism. So this whole saponification mechanism is very similar to this. We're just replacing OR with CX3 as a leaving group. All right. So the take-home message is phenols. Apparently, I don't like cheap expo markers. Kobe. So the take-home message is enols can be electrophilic, and enols are nucleophilic, and they can attack good electrophiles like protons and X2. Br2, Cl2, and whatnot. And so if you want to do chemistry on an alpha carbon under acidic conditions, you can, but mechanistically speaking, it's going to go through the enol. Whereas when you want to do functionalization of carbons adjacent to carbonyls under basic conditions, it's going to go through the enolate. And the enolate is going to be much more reactive than the enol, because an enolate has a minus charge. And so it's going to be more nucleophilic because it's an anionic species. And we're going to now shift gears now from doing things that both enols and enolates can do to now talking about chemistry that only enolates can do. So enolates can attack worse electrophiles. So enolates are a lot more reactive, so they can attack less electrophilic things. And just to show you an example, enolates can attack alkyl iodides. So enolates can do classic SN2 chemistry. Enols, not as well. So you take a strong enough base, and you get your enolate. That can attack good SN2 electrophiles like alkyl halides. Can someone give me an alkyl halide? Any alkyl halide will do. Methyl iodide is a great one. And this can probably occur at room temperature. So there's CH3I, methyl iodide. So an enolate can fairly easily, since it's an SN2, let's draw our sigma star bond. Let's draw like a tetrahedral carbon. So an enolate can attack alkyl iodides into a classic SN2 chemistry, giving its electron density into the sigma star orbital of an alkyl iodide. Giving us an alkylated ketone. So you can alkylate ketones under SN2 conditions from the enolate. You need to be from the enolate. So what that brings us to is, well, how do we make enolates? How do we make enolates? And we're going to start by talking about how to make enolates by starting with the hardest case possible. That way, everything else will be really simple. And the hardest case possible is hard because it brings us back into contact with the good old friends, kinetics and thermodynamics. In this class, we're not going to get away from kinetics and thermodynamics. In chemistry, you're not going to get away from that. So, in the hardest case are non-symmetrical ketones. So here's just a generic non-symmetrical ketone. So it's a ketone that has one alpha, it has one of the alpha carbons having two hydrogens, and the other alpha carbon having one hydrogen, and some kind of substitution, like an alkyl. So in this class, there's two bases we need to know. One of them is a nitrogen with two bulky isopropyl groups. It's a deprotonated amine, so it's got a minus charge. And its counterion is a lithium. So this molecule is called lithium diisopropyl. So lithium for the lithium, then diisopropyl for the two isopropyls. Amine. So lithium diisopropyl amine, its abbreviation that everyone uses, because lithium diisopropyl amine is kind of a mouthful, is LDA. So this is LDA. So how basic is lithium diisopropyl amine? Very basic. Give me the pKa of its conjugate acid. 35. How about 35, right? So amines, neutral amines with one hydrogen. That hydrogen's pKa is about 35 to 38. And so the conjugate acid of lithium diisopropyl amine has a pKa of 35. So pretty basic, right? Very basic. So then these hydrogens, these three hydrogens in this ketone, their pKa's are roughly, we mentioned this earlier 5 minutes ago, roughly 20 to 24-ish. So let's call these pKa's 20. Let's call this pKa 35. So we have a 1 times 10 to the 15th difference in pKa's. Or this is 1 times 10 to the 15th more basic than these are. So I drew this as an equilibrium error. However, what would the more realistic equilibrium error look like? Like this, right? By 15 orders of magnitude, this is going to favor this acting as a base and deprotonating the hydrogen. So with lithium diisopropyl amide, the deprotonation is irreversible. So it happens once, and then it stays. So does that sound like it's a kinetic or a thermodynamic base? If it's irreversible, is that going to be kinetic or thermodynamic?
Kinetic.
If it's irreversible, is it going to be kinetic or thermodynamic? Kinetic? Thermodynamic. It's going to be kinetic. If a reaction is irreversible, or under the conditions of the reaction not able to go backwards, the thing that forms first is going to be the major intermediate. So if it can't go backwards, it can only go forwards, it's kinetic. So if a reaction is irreversible, it's going to be kinetic. Alright? And so which one of these hydrogens do you think is going to be the one that this base, so one of these hydrogens deprotonation, so deprotonating one of the carbons, will give the kinetic and the other one will give the thermodynamic, not to spoil anything. Which one of these deprotonating hydrogens in this carbon or deprotonating hydrogens in this carbon do you think will give you the kinetic product? One's in the right? Why? Okay, so sterics. So sterics are number one, so easier to get to is just a way of saying sterics, right? And the amine is, diisopropyl groups are very sterically large, and so it will be easier, especially at cooler temperatures like -78 or 0 degrees, if there's less energetic penalty to go for this hydrogen than this hydrogen. So if it tries to go for this hydrogen, it will form a steric interaction with this methyl group. If it goes for this hydrogen, it won't form a steric interaction with that methyl group. So energetically speaking, so if we start from the ketone, so 1, so if this is 1, which of these transition state energies will correlate to deprotonating this hydrogen? It will be this one. Because when this bulky base tries to take the more substituted hydrogen, it's going to form a steric interaction, which is going to give us an energetic penalty, which is going to make the transition state higher in energy. So LDA will do the lower energy deprotonation and form the less substituted enolate, which is the kinetic enolate. Less substituted enolate, kinetic enolate, LDA. That could be 50 points on the exam right there. Kinetic enolate. So the less substituted enolate, which comes from an easier deprotonation by a bulky base at this hydrogen, will give the kinetic enolate, which is going to be the less substituted enolate. Conversely, if you use a weaker base, and then the weaker base in this class we care about, sodium ethoxide. So the conjugate base of ethanol. What's roughly going to be the pK